Hello, uh, everyone. We were discussing about the special cases of Routh array formations. So, in our last example, we have considered one polynomial, that is characteristic equations, where we have seen that there is a problem with the particular row where all the elements becoming 0. So here also this problem is again same kind of problem. Here we are taking a sixth order system, that is a polynomial characteristic equation sixth order is taken here, and we have formed this Routh array like this. But the similar procedure we have already discussed. Now s to the power 6, s to the power 5 and so on. And see, this is 2, 12, 69, 0. So we may just divide the all elements by 2 and you get 1680. Similarly, when you have formed this s to the power 4, you can also divide this by 2 to get 1680. And as these two rows elements, that means s to the power 4 and s to the power 5 rows elements, 1680, 1680, definitely this row is to the power 3 contains all the elements 0. So this falls in the same category. And once this kind of problem arises, what we have to the Routh proposes is that you have to consider one auxiliary equations containing or considering the previous row, that is containing the row of s to the power 4. And what is the elements of the s to the power 4? You see, this is 1680. So auxiliary equation will be equal to s to the power 4, that means the coefficient of s to the power 4 will be 1. Next, one step, that means the power is actually reduced by 2. So s to the power 2, 6 s to the power 2 plus, you see, 8 s to the power 0. That means auxiliary equation becomes s to the power 4 plus 6 s square plus 8, right? And this is a fourth order polynomial. Now our aim is to find the value of that is the finite number of finite values of elements of this particular row. So to avoid this 0 0 0 0, what we have to do, we have to just differentiate das and ds once. So you will get 4s cube plus 12s plus 0. That means 4s cube plus 12s. And now these are the coefficient of s cube and coefficient of s. So we may put instead of 0 0 and all this, so we may write instead of this will be your 4 will be your element, and next element will be your 12. So we get 0 0. Now this element is not having any problem, so we can continue to form the completeness of this for the completeness of this Routh array, right? And now the similar procedure, once you will get right, this is 4 and 12, so this can be divided by 4, so you will get 1 3 0 0. So this is 1680, this is 1300, and you see the coefficient of s to the power 2 will be equal to 3 8 and 0 0. So once this is 3800, s to the power 1 coefficient, this will be 1 by 3 0 0 0, and this is equal to 8, that you can form, right? Now what is the difference between this problem? Already we have derived in the last class for the same special cases. In the last class also we have derived one example where calculated one or solved one problem where we have found that there was, after completion of this Routh array, there was the first column elements where there was a single negative element. So once if negative element is present in the first column, so the system is unstable, there is no problem in it. But here you see all the elements of the first column. What are the different elements of the first column? You see 1 1 1 1 3 1 by 3 8. Here in this case we found that all the elements here, all the elements positive. So should it be like the system should be stable? No, that is the question. If after using the auxiliary polynomial auxiliary equations, you get the completed Routh array and find any negative element. The system is unstable. If you find all the elements positive, then the system will not be stable. This is not stable. This is marginally stable. Okay. So if there exists any row having all the elements 0, and if all the elements of the completed Routh array, that is first column of all the elements of first column are positive, the system is marginally stable. That is not the absolute stable, that is the marginal stable. And once you know it is marginally stable, definitely there exist some roots or poles on the imaginary axis. So these are the, maybe there are another poles which are lying on the imaginary axis. This is the concept of stability, already we have discussed. So here also we will find some of the poles which will be lying on the imaginary axis, and once the poles are lying on the imaginary axis, what happens? The system nature will be oscillatory anyway, which is known as condition of sustained oscillations, right? This is the condition for sustained oscillations. This is condition for sustained oscillation. Once the sustained oscillations is obtained, definitely you will be having some frequency of oscillations, right? So next step is that we will having the marginal stable, that there is no confusion in it. Now we have to find the whether there is any roots exist on the imaginary axis. There must have the roots which will be lying on the imaginary axis, and if the roots are lying on the imaginary axis, definitely there will be some frequency associated with it. How to find out it, that we will discuss here. So this part I am just removing, and you see there is an auxiliary equations, and this is a fourth order equations. So to get the frequency, we have to make auxiliary equation is equal to 0, because this is a conditions where also the poles locations has been changed due to overcoming of this stage. So what you have to do, s to the power 4 plus 6x square plus 8 must have to be 0. Okay, so you see this is fourth order equations, and here easily it can be solved like plus 8 equal to 0. That means s square plus 4 plus 2 s square plus 4 equal to 0. Here you see s square plus 2 into s square plus 4 equal to 0. So this is 0 and this is also 0, right? Once these are 0, so s equal to plus minus root over minus 2, that is minus plus minus j root 2, and here s is equal to plus minus root over minus 4 plus minus j root over 4 plus minus j 2. Okay, so 4 roots we find, plus minus j root 2 and plus minus j 2. These are the 4 roots. So in the S plane there may be poles like this, and there may be poles like this. That is the pole locations. You see, the pole locations are on the imaginary axis. So definitely this is marginally stable, and this proves like this. And once you see the locations are like plus minus j root 2 and plus minus j 2, so how to find out the frequency? And you know the equation of the S plane. We know the equation of the S plane is like, I can write the equation of the S plane. So what will be the equation of the S plane? Equation of the S plane, you see this is sigma plus minus j omega, and this is your real part. So here what are the poles you are getting? J root 2. So 0 plus minus j root 2. So this is your frequency. So omega is equal to root 2 radian per second. That means the system may oscillate with the frequency of j. Omega is equal to root 2 per radian per second, and from this part again s is equal to 0 plus minus j 2. That means the frequency may be 2 radian per second. So this system we are dealing with may have two frequencies. One is √2 radian per second or 2 radian per second, right? So this is the way how to handle the situations when there is a row which contains all the elements 0, right? And the next special case we will consider where we will see if there is any element in the first column which is 0. So how to overcome that situation and what is that situation we will describe in the next section. So let us consider this case 2 where we have considered a fifth order polynomial, right? So you see this fifth order polynomial that is q is equal to s to the power 5 plus 3s to the power 4 plus 2s cube plus 6s square plus 6s plus 9 is equal to 0. Now with the similar fashions we have considered the Routh array, and till the row containing s to the power cube we have considered and found that this is 0, but this is positive value or some value, and this is also 0. So this is the difference between, there is a difference between the previous case. Previous case was that a particular row, maybe say these all the elements were 0 like that, but here you see only the first element is 0. Rest of the elements may be finite, that is positive or negative. Here this is positive. So the pivoting point is that this is the pivoting point, that is it is a 0 in the first column. Once you get 0 in the first column, see what happens. So 0 into 2 minus 1 into 3 divided by 0, because all the elements you have to divide, all the elements will be obtained by dividing in the first element of the previous row. So here it is 0, so this construction is not possible. So definitely there is a problem. So in that case, what is the procedure to bypass this and to solve this problem? So for that purpose, what Routh proposes that consider this very small quantity epsilon which tends to 0, right? And see, if epsilon is a very small quantity greater than 0 and tends to be 0, that means this is tends to be 0, but that is positive, that may be negative also. But here for the Routh array consideration, this very small quantity epsilon which is taken to be tends to 0 and this is taken to be positive value, right? So once this is a finite value and very close to 0, then we will just bypass this value with small term epsilon, and this is 3, this is 0. Now considering this to be epsilon, we have to consider, or we have to form the rest of the array. That means you see this will be 2 epsilon minus 3 by epsilon, right? And the next part is 3 0. Next you see this is 3 minus, this is your 3 into 2 epsilon minus 3 by epsilon minus 3 epsilon by 2 epsilon minus 3 by epsilon. This is the quantity s to the power 1, and this is 0 minus 0, this is your 0 and 0, and last element this into this minus 0 by this, that means this will be your you see this is 3. So the Routh array can be formed with the help of a small quantity epsilon which tends to be 0, considered very close to 0 but not equal to 0, and this is positive quantity, right? So if this is positive quantity, and you see what you are getting at the first column of the Routh array after considering this epsilon. So first column of the Routh array, this is simplified at like this. What we are getting, this is 1, this is 1, this is epsilon, this is 2 epsilon minus 3 by epsilon, that means we can write it 2 minus 3 by epsilon, right? 2 epsilon by epsilon means 2 minus 3 by epsilon, so 2 minus 3 by epsilon, and this will be are equal to your 3 minus 3 epsilon by 2 epsilon minus 3 by epsilon. This is the quantity you are actually getting. So that means basically you can write it as a simplification part. So this we can write like, you see, this will be 3 epsilon squared by 2 epsilon minus 3. So we will just modify this part for better representations. So we can write it like 3 minus 3 epsilon squared by, you see, 2 epsilon minus 3. So this is 2 epsilon minus 3. So this is your term. Now you have to find out whether all the elements are positive or all the elements are negative, or any elements is negative. What is? So this is positive, this is positive. Once epsilon is taken as positive, so this is again positive. So see, this is positive, and this is positive. And when epsilon tends to 0, so 3 by epsilon is very large quantity, right? So 3 by epsilon, here you see 2 minus 3 by epsilon tends to 0. That means this is a very large quantity, and 2 minus very large quantity gives you negative value. So this in turn will give a negative value, right? And what about this? If epsilon tends to 0, that means this is 0 and this is minus. So this is nearly equal to limiting value of it tends to 3. That means this is positive. So limiting value is 3, positive. Limiting value when epsilon tends to 0, if you put the limit on numerator denominator, you get this close to 3. This is positive and this is negative. So what you have found? You have found there is a sign change because there is a negative element in the first column of the Routh array. Once there is a negative element in the first column of the Routh array, system is unstable, right? So system in this case is definitely unstable system, because as we know, any element in the first column, so element in the first column, one element negative, so system is unstable. Once the system is unstable, you have to find out how many number of poles are right hand side of the S plane. So positive to positive, no sign change. Positive to positive, no sign change. Positive to negative, one sign change. Negative to positive, one sign change. Positive to positive, no sign change. So number of sign changes. So number of sign changes 2. That means 2 poles at right hand side of S plane, right? How many poles are there actually? 5 poles. So 2 poles are the right hand side of the S plane, means 3 poles maybe on the left hand side of the S plane. So is there any row containing its first element 0, but other than the first element all other elements are present? So in that case you have to bypass this by considering epsilon, which very close to 0, or replace the 0 by epsilon, and that to be considered as the positive value. So based upon that, you just construct the complete Routh array, and from that you find out which of the element at the limiting case epsilon tends to 0 is positive or negative, and rest of the things are same. Okay, so this is the way how the special cases of the Routh array formulations has been worked out, and the problems of to the different kinds of the solution of to the different kinds of problems can be solved. Okay, now these are all about the absolute stability. Now we are going to get the concept of relative stability by using the Routh array formations, that I will discuss in the next class. Okay, thank you.